I'm Frank Rausche, and I graduated in 1970 here at Case. And in what I'm going to talk about, some of the history of the PILE project, as we called it, you will see that I'm talking sometimes about what we did at Case and what we did later at our companies, QRL Engineers and Power Dynamics. These things kind of morphed into each other. And we really did a lot of research still after we had finished that case, after the PILE project was finished, and developed things that here had started here, developed them further, together with quite a few of other graduates from the school. So I will be talking about something that started at the university here. It was actually Case Institute of Technology at that time, and then morphed into the actual applications on the construction sites and was quite successful in doing so. So I'll talk about this PILE project that was the foundation, and that's a kind of a pun, of course. Piles are used for foundations. Foundation for what we're doing today, a little bit about the history, the methods, and then getting also into some of the things that we're doing today, further developing today and applying today. So first of all, you might ask, maybe in case everybody knows that, but you might ask, what's the problem with those piles? Why did you have to study things? Well, pile driving was the thing at the time when I started. And so you have a stick that you have to get down in the ground. And how do you do that? You use a hammer and smash it and get it down in the ground as far as you can. And when it is arriving, then it's good. And if it's going deeper and deeper, then many people will come to the construction site and wonder what to do. So there was, because static testing to determine the capacity is too expensive and takes too long, there was always the so-called energy or dynamic formula being used. And every professor that had a consulting job and did the job at a certain construction site came up with his formula. And then you could, with that formula and given a blow count, number of blows per inch or per foot, you could determine your bearing capacity of the pile, the so-called bearing capacity. And depending on the formula, you get one or the other result. And our friends in Sweden always said, if you have a capacity and have a blow count, you can always find a formula that gives you that value. So you don't have to worry about being wrong. So then that was, of course, discredited. Everybody knew it wasn't good. Contractors actually liked it because it's very simple. And calculating with a static formula was already considered a little bit too complicated. You had to know soil properties. And then at the end, it was disappointing often because the static formulas didn't work out very well either. So things that we had available were unreliable. Oops, that was the wrong direction. So Perry Nara, at that time in the late 50s, early 60s, was associate dean here at Case. And he had a project where he had to study some, for the Defense Department, some projectiles being fired into the ground. And the question was, how far would they go? And he studied that by having a mass penetrating into the ground and measuring the deceleration and calculating the resistance from that, according to Newton. And being a civil engineer, he probably didn't like what he did so much there, and he knew about the piling project, and he said, would be good to instrument the pile driving system, measure the deceleration, and come up with a pile capacity. And then you would put that in a little computer on the construction site, and for every hammer blow, you would get the bearing capacity of the pile. So that was an idea that really was of interest to many people, including the Ohio Department of Transportation and the Federal Highway Administration at that time. US Department of Transportation. And so they funded a study, and Professor Scanlon and Professor Goebel jointly were principal investigators and brought this project further. Several graduate students already get some theses done, among them, for example, Bill LaPay did a literature study that was part of the deliverables of this study. Of course, instrumentation had to be developed, and the pile capacity computer, as it was called then, that was done by a student from the computer science department. And then, of course, we had to collect a lot of data, both static data and dynamic data for comparison and verification, and then both on reduced scale piles and on full scale piles. You see here a picture of myself holding on a reduced scale pile, 3-inch diameter, 25 feet long. These were actually real piles. They carried up to 12-ton load. And so we had to move things around. John Tomko, who later became professor at CSU, was the graduate student that worked on his PhD before me, and he had already devised a movable static load testing system. And then there was, of course, also a pile driver. You see that in the middle picture here. And there were gauges put on the pile, subfoil gauges and accelerometers attached. And that all these signals went into our van that we had. And you see here on the left-hand side, the instrumentation package that we put together eventually. In the left upper corner of that photo, you see the first version of a pile analysis, what we call analyzer. And at that time, it was still called the pile capacity computer. That was a digital unit at that time. Unfortunately, never really worked very well. And so later it became an analog computer that an undergraduate student, a very gifted and talented young man, Peter Hajek at Case, which he then further developed. So we had to not only, of course, measure things, we had to also work on that method, the resistance method. Now we measured the force too, so our resistance formula became force minus mass times acceleration, again, pure Newton. And then we had to assume a soil model. In that case, you do mathematical series. That's a soil model. So that soil model was a power series in terms of velocity. The first term there was, though, the R sub 0 a static value, really, and the remainder were all parameters multiplied by velocity and velocity squared and so forth. The idea was when the velocity is 0, then you get your static capacity, R0. So John Tomko studied that further, and you see here our full-scale testing site in Akron at that time. The I-77 was then being built. We had to have some whole crew of undergraduate students helping us because there were things to be carried and held and read and moved. So there was a lot of work to be done. And we learned a lot on the construction sites. We learned about what those contractors really have to do to get a building built, what goes all into that. There's a lot of really creative work going into the contracting on the construction site too. We learned about the pile driving hammers. We learned about piles. We saw that the soils are really difficult to deal with. They have a totally different resistance during driving than after driving, so you had to do restrikes. And things like that we had to learn. Keep our fingers away and learn a little bit of safety. I always say if OSHA, of today's OSHA would have been around when we did that work, we would be all in prison still because everything was forgotten what we did then. So there's another thing that we did, and that's why we need the muscle guide too. And that was a so-called top transducer. You see it here. George Goebel actually had designed that and is really a pipe instrumented with foil gauges. So that had to be put on the top of the pile. We did also build some piles in the lab that was still at that time in Olin building at the basement. There we had some facilities to test then our piles that one pre-stressed concrete that we built, the other one a steel pipe. And we did some measurements there. Really measuring on the construction site was the thing to do, and we learned a lot there, much more than from doing something in the lab. In a picture that I showed you before in the instrumentation, there was our output instrument. The output instrument was a so-called visicorder that had galvanometers that wrote on a light-sensitive paper the signals that we then had to interpret. And this visicorder spewed out the paper at 2 meters per second. There was a job in the coldest part of winter in Richmond, Ohio, and I was sitting inside the van, and they said, okay, we're gonna start, you have to start that visicorder. And I didn't want to waste too much paper, so I was waiting for a hammer blow. Hammer blow came, I pushed the button, paper came out, there was no more other hammer blow coming. Why not? Well, they were all running away from the hammer because they were afraid it comes out on top of the hammer. So after trying that several times, I hadn't collected any data yet. I managed to just let it run and get one hammer blow on our, I don't know how many meters of paper. Again. So we had to digitize then. We have to find this little bitty scribble of galvanometer trace on the paper. We had to digitize then. I invented a device to do that. It was a little transparent grid with 1/60th of an inch grid on it. And so we had to look through on our points that we had put on the trace. And then we punched it on cards and went to the UNIVAC computer and put it in there where we could plot it. So there you saw then the plots of force, velocity, displacement, force together with the resistance on the bottom. And so we collected data. Already when I came in '66, a few pieces of data had been collected on construction site. And this is something that then was analyzed by John Tomko with our phase 1 method. And then the phase 2 method was one where he did some averaging. And things look very good for sand. For clays and silts, they were not quite as impressive as far as correlation is concerned. So we discovered that there was a problem with that formula, and we had to look further at it. And in the meantime, Professor Goebel had gone on a sabbatical to Berkeley in California, and Fred Moses, Professor Fred Moses, took over as my advisor, and he said you should really study the traveling wave concept, in other words, wave mechanics. And so the literature that Bill LaPay had collected had a lot of papers about that. I read that, and then I realized we really had to work with the wave speed c, because there is a stress wave traveling down the pile if we hit a hammer very suddenly on top of the pile. There's a stress wave going down, coming back, and impedance, the pile impedance was a very important quantity too, because if you now plot it with considering the impedance, then you will see that these curve suddenly makes sense. Force and velocity going up together in the beginning at the time of impact, and then separating as resistance from the shaft of the pile is being encountered, causing reflections, which then will produce a difference between force and velocity that can be interpreted as the shaft resistance. So that was quite a breakthrough. And with that, then investigating traces like here, this offshore trace where we had a long pile, made it even clearer what we saw. For example, here on the left side, until the point where the penetration of the pile in the ground was encountered, above that being water, we had throughout that proportionality between the two curves, and only a deviation from force from velocity where the pile penetrated. That was actually a record that we already then collected as consultants. It was on the Heather platform where I was in '76, and where we had the first time offshore a pile driving analyzer working. So that analyzer was, of course, the other deliverable that we had to develop. And there is the phase 1 computer that had undergone very serious surgery by our undergraduate electronics and computer systems student. And so then we came up with a new formula based on the wave propagation, which you see written underneath those computers, where practically we're now taking force and velocity at the time when the wave goes down and at the time when the wave comes back. So input and output are practically compared, and that gives us the resistance. And then because Tony Sada was not very happy what these structural engineers were doing there, we put a PI knob on the thing. And when the plasticity index was high, then we shifted the time where we took these records to a later time, and we got a better agreement than for the fine-grained soil. So then further work had to be done, and it occurred to us that this whole time of zero velocity doesn't really work very well. So we took instead a maximum time of the record, and then introduced a damping factor like other people had done with the wave equation. And of course, you know, in deference to our dear alma mater here, we call that the case damping factor. It was a viscous damping factor divided by the pile impedance. So that actually didn't make much sense as far as the soil is concerned, but it worked pretty good otherwise. And so the whole world talks about case damping factor, and everybody wants to know what the case damping factor should be now. Yeah, it became quite known what we were doing. This analyzer on the upper, well, the right-hand side, is already a commercial product. It's still an analog computer, and it produced already something like an energy value, transferred energy, by integrating the product of force and velocity. But we wanted more, and we got more with a digital computer. That came out in the early 80s, and it was based on a Motorola integrated circuit. And it allowed us then, by further developing equations based on wave mechanics, to calculate things like a damage number. And so if a pile had a damage or a reduction of pile impedance, as we would call it then, that could be quantified. We got, of course, the shaft resistance, and also printed out by the analyzer the tension force in concrete piles, which is there very important. So that was quite a development once we had it in a digital form. I would like to go back to one more thing that we did at CASE, and that was instrumenting piles. I had mentioned already that reduced CO pile that was there, driven actually at West 14th Street, right next to I-71. It was a leftover piece of property that the ODOT people had, and it was a sandy soil there. And this long stick, 25 feet long, was instrumented at 3 different places and at the toe, so that we could measure what's happening along the pile at the toe. The left-hand picture then took the toe instrumentation, acceleration and force, and integrated the acceleration to velocity. And so you see here the displacement when we integrate the velocity. And the maximum displacement here, of course, would be the time when the velocity is 0. So you see the static curve here that we, during a static load test, had determined from our measurements. And you see the dynamic curve here. And really, at the time of 0 velocity, we have a pretty good agreement between the statically measured resistance and the dynamic resistance. So then we went, of course, to the construction sites in Toledo, where they have a terrible clayey silt, and we measured this here on a 30-inch diameter typical ODOT pile, a 12.5-inch, I'm sorry, inch diameter pile. And you see in that silt, we have much higher dynamic components in the beginning. We get a lower value afterwards, after this explosion-like resistance that happens during the first encounter of the wave at the bottom. And then the resistance starts to increase above the static value. So that is one of the problems that we did face, and that is still sometimes giving us some problems. So that is a problem that can be partially at least solved with choosing the right damping factors. And Garland Likens, he did a lot of work, very good work, and actually preparing a table based on soil type that gave us the different damping factors, case damping factors, which varied between 0.1 for a sand and 1.0 for a clay, for example. So another thing about velocity of penetration, because I'm a case, we have to make it a little bit more complicated. Otherwise, all the students here start yawning about what this old-fashioned stuff is all about. Anyhow, there's a plot here that shows little dots, red clay, yellow sand, collected at our competitors in the piling area, the Texas A&M. We always looked at each other. They were working with the wave equation analysis. We did the case method. And at the end, we came all together. They started measuring and we started doing wave equations. But anyhow, they did some impact testing on dry axial samples and measured the forces during that impact and at certain velocities at the bottom here. And so they were doing it with typically 5 to 10 or so feet per second, which is at the lower bound of what we encountered during pile driving. And for example, the SPT testing method also is right here. There is the speed with which your cone penetrometer would penetrate the ground if you do that testing. And here would be a static load test over there at the very low end. If you extrapolate these clay lines, you come to a static, you have to really test at a very low speed to come up with a static value directly. If you tested it at a higher speed, you would definitely come up with a lower value, a higher value of resistance than the static one. And for the sand, it looks better. The sand already at the CPT speed would give you a 1 times static resistance. Interesting was when we did our casework on the reduced scale pile, we once did a slow CRP test, and then we pumped the jack as fast as we could, and then we got this point here. That was the static one, and then this was our point from our dynamic test in these silty, in the clayey silts. Okay, well, in the meantime, and that is now much later, we had further developed the pile driving analyzer. This gentleman here looks so happy because he just got his wireless PDA, as we called it now, pile driving analyzer, testing this pile back there over water, so there's no more wire going there. And here's somebody from GRL, from our company now, with the newest piece of equipment, also wirelessly, and you see the radio that transmits the data here. Did I do that? No. There we go. So I am disabled. Is it my age?
That's right now.
Good work now?
Yep.
I don't know what you did, but it's fantastic. Anyhow, so here is what we are getting out as a result these days. For every hammer blow, you can get the forces, you can get the stresses, you can get the velocities, and of course the resistance for various damping factors if you want to select later on. And then you get a statistical summary, and finally you can make pretty plots. It's all of these things either versus depth or versus blow count. Of course, I had to make it more complicated yet. The case method itself, it wasn't enough. I had to do a model of the whole pile, get the shaft resistance directly calculated using the Smith lump mass model that is used in the standard wave equation analyses. I was able then to calculate a static resistance after matching the force given the velocity as an input, and you see in the upper right-hand plot, you see the force match, and you also see the proportional velocity graph with it. And then you come up with you use the calculated shaft resistance with a static value of your calculated static load set curve or load displacement curve, and you can compare that with a statically tested one. And we're claiming now that you really don't need the static that often anymore. So this agreement then allows us to determine the appropriate case damping factor for the case methods, which we can then calculate all the other blows. The other thing that we can plot is a nice picture of the waves traveling down the pile and back up. So that's length coming out of the plane here and time to the right, and you see a wave going down to the bottom of the pile and being reflected towards the top again. So that looks kind of nice, and this is what we really calculate with various segments along the pile. This is now the summary of TAPWAP these days of the case pile wave analysis program. On the going counterclockwise from the upper right, it's the data that we have measured, the force match that we have computed, then comes the static, the calculated static load displacement curve and the resistance block. So that can be even then repeated for several blows in a row. Is, for example, you do a restrike, or you do like shown here, a dynamic test on a drill shaft where you only apply maybe 3 or 4 blows with a pretty big weight. This is our so-called apple here, going back to Newton, of course. With that apple, we are hitting our pile top, our pile head, as everybody calls it also. So then we can plot, if we apply, for example, growth with increasing energy, kind of an envelope Sorry about that. Yeah, an envelope of these calculated load displacement curves. Well, this all had to be disseminated, this knowledge, and already in 1969, Professor Goebel invited here to Case. We were at, I believe, in the Bingham building already. He invited some people from the industry. The other graduate students kind of envied me that I already had a foot in the industry with that. Well, there were 2 or 3 Ohio contractors, and it didn't really make too much of an impact at first. But this dissemination of our knowledge was key to also create interest not only in other states, where we also started to do some demonstration testing, but also to go to other countries with it. And we were then approached even from Mexico and from Canada. We did very much work in Canada to do the testing there, and eventually to give them also some equipment to do it themselves. So this is actually not a case anymore. Professor Goebel had gone to Colorado already in '77, and I don't think he called it a case pile seminar there anymore. That was the CU now in Boulder. But in any event, the idea was the same. And we did it also a lot of new users and contractors, anybody in the industry. Not everybody was all that happy. This is a sketch from somebody who had attended our talk. So just a few time. I don't know if I'm over. I started a little late. I had some slides here with some additional developments. I want to talk in particular about the problems we're facing right now with the wave equation analysis, and then the associated static analysis and the so-called SRD. Now, the wave equation analysis, as I had mentioned occasionally, is one where you actually tend to replace the dynamic formula with a more sophisticated pile model and also soil model. And you create a bearing graph again that tells you for a certain flow count the bearing capacity. And as you can see, for example, with the 2 curves that we see in the lower plot here, which is named bearing graph, you can see here that for 2 different soils, for example, we get 2 different results, which with the formula you wouldn't get. So this is something widely accepted. Federal Highway Administration actually supported us in developing a version of it, again in competition with TGI at Texas A&M. That had been already much longer in that field, but we were able to verify this wave equation program with our data that we had collected and make a diesel hammer model, which was around here, the hammer of choice. And then I just want to mention that program uses another damping factor, yet the so-called Smith damping factor. Anyhow, oops, what did I get wrong this time? Okay. This, when I talked in 1974 to the German engineers, they said, oh, this is all boring stuff. Nobody is using driven piles anymore. So why do you tell us about that? And now it turned around. Now they're very interested in Europe because they want to spend $80 trillion on driving these monopiles, as they're called, down in the ground for the wind turbine industry. We're starting here now. One in our office has already done a drivability analysis for such a, I think, almost 30-foot diameter pile offshore New Jersey. So there's a lot of money involved here. Every hour of one of those ships there doing pile driving costs probably around $1 million. So you want to be quick and you don't want to have early refusal or anything happening to that pile during driving. And drivability is the thing to do. And there are some impressive pictures here of a water hammer that the wave equation analysis I wrote for them predicted it wouldn't work. And indeed, it is discontinued now. Anyhow, when we do wave equation analysis for drivability, we have to calculate beforehand the resistance that the pile has during driving, the so-called SRD. And that is the one that we always measure at the end of driving. And if we measure then sometime later during a restrike, we get the so-called long-term resistance. And as you can see, the long-term resistance is generally much more than the static resistance to driving in the beginning. And what one defines then is the so-called setup factor, which in our practice, if we don't know anything better, is 1.2 for sands and 2 for clays. And so we would calculate with a static formula the long-term resistance and then apply our setup factor to reduce that capacity to a SRT value. So an example is given here, and our program, thanks to Dr. Liang here and Dr. Quan Go, he's not here right now, but they have programmed now all of these various status formulas into our wave equation program. And you can see, depending on what we are choosing, if we're choosing the FHWA recommendation, that's the black line going way out, and we're much higher with our SRT than we would be with some of the other formulas. Of course, it's not made for offshore, for example. And so then when you calculate the blow count, then of course you're also quite different. And for example, your driving times would vary between 8 and 25 minutes that you're calculating. Now everybody says around here in the academia, don't use SPT or these other formulas, that's nonsense. And so you use CPT, that's much better. And granted, CPTs are the thing to use if we have those results. And these methods B through E were specifically made for offshore pile driving. So they are the darlings of the industry now. And you can see the different capacities, SRD, and then also calculated blow counts that you might get from these different methods. So there's always a variation. The newest darling in Europe is the so-called friction fatigue approach, where it says that you have during driving always the initial, which we would call probably the long-term resistance at the pile toe, but further up, the resistance gets worn down, fatigued. And so near the mud line, it would be a much lower value. So they have, for example, for sand, a ratio of 5, which in my mind means that the CPT prediction that they make is way too high, but that you don't tell people that love the CPT so much. Their results also show you what you can expect offshore as far as CPT readings. These are the final lines, and then what they predict with their method. And it has, it must be granted, where it is very attractive in certain areas of the world to use that for the prediction. So we have a problem. You know, the SRD, the end of driving resistance, plus a damping value and times velocity is a higher dynamic resistance. So during driving, you actually have a total resistance which is higher than the static one. At the end of driving, you have a low resistance, and after some waiting, you have a higher resistance. So now it would be nice, and that's what actually many people hope for or believe, that the long-term resistance would be equal to the dynamic resistance, because then we wouldn't have to worry anymore about a damping factor and all of these complicated things. But that doesn't work, unfortunately. And it is challenging to come up with the right damping values, with the right predictions of the long-term resistance. Fortunately, it's all working out real well and linear in the semi-log plotting. So as long as you know what to do with semi-log, if you're technical engineer, you're good. You always come out right. Now, it leaves me alone again. It is not all that easy, though. We have all these different methods that I discussed kind of real quick, and they are cheap from the top down to the bottom, much more expensive there. And the quality, of course, improves with cost, and none of them agrees with each other. So what do we do? Garland Likens will tell you what to do about that. He will solve the problem finally. All right, so thank you, Case. Thank you for letting us learn here, letting us research. And just to tell you, the Case method and the CAPWEB are now used throughout the world on by thousands of engineers and construction sites. Your name is being known, at least in the deep foundations industry. By the way, you see here Professor Sada in the good old times. We had always a great environment of learning and helping each other, and that brought us forward in this research. And now, Case graduates, as you are here and see this talk, we need you. We need you to study and learn, but then you need to come to us and see if you want to work with us. Thank you very much. And thank you for the honor of talking. Let me talk to you. Any questions? Any questions? Please feel free to bring up. This is thank you very much. When did that one go? Yeah, that one.
Thank you, Frank. Now we'll try to figure out, and he's already put the blame on me, so we'll try to clean up the mess. Okay. University researched application, and you've seen, cloud writing analyzers now used throughout the world, really. Allowable stress design is used. allowable stress design is used in private practice in the United States as sort of the rule of thumb. We have that the resistance has to be greater than the factor of safety times the applied load. And the International Building Code has put that in there starting in year 2000, that we use a safety factor of 2, and whether you use a dynamic test or a static test, factor of 2 is what is being used. For the Federal Highway Administration, they had a lot of smart people sitting in the room. They called it the Delphi method, which is like the Oracle of Delphi, that they just sort of grab numbers out of the air as they sort of feel led to do. And they made the observation that, if I can figure out which one the pointer is, okay, that the safety factor should depend upon how you determine what the capacity is in the first place. And as Frank has pointed out, the dynamic formula doesn't work very well, so you get a relatively high safety factor. And static load testing, there's the 2. And if you do static load testing plus dynamic testing, they give you a little bit more benefit on that. So let's do a theoretical exercise where we have a total load to support, that's dead load plus live load of 4,000 tons. And let's say the ultimate capacity per pile is 200 tons. Well, if for the dynamic formula, using a safety factor of 3.5 into 200 tons means I have a design load in tons per pile of 57, and 57 tons per pile, and I have to carry 4,000 tons means I need 70 piles. And as I have a more accurate method, I get higher loads per pile, and that requires fewer piles per the foundation. So you can see right away that there's an economic benefit for doing a better analysis of what the capacity is. And if you do testing, whether it's dynamic testing or static testing, there's quite a bit of savings. Most of the cost of the pile project is in the material. So if we can eliminate piles, we have eliminated cost. Well, not everything is an allowable stress design. The Federal Highway Administration in 2007 started mandating that the state highway departments start using something called load and resistance factor design, where now we have factors that we apply to the resistance, P factor, and factors that we apply to the loads, dead load, live load, wind load, earthquake loads, etc. And in various combinations. So really that allowable stress factor of safety has been now split into load and resistance factor designs, load and resistance factors. And if you equate the resistance and rearrange those equations around, you see that for the allowable stress design, we have the dead load plus live load. We'll talk about that one case right here. And for the LRFD, with the primary case, dead and live load, with different factors on the dead and live, because we know the dead load very well, we can calculate that. We have a volume of concrete, volume of steel, whatever. And so there's a relationship between the factor of safety and the P factor for LRFD that you can easily derive. So let's take a look at the same example using the AASHTO LRFD factors. And now we have P factors that are small for the formulas and large if you do static load testing. And you can calculate using that formula with a P over L ratio, typical value of 3, what the equivalent safety factors are. And now you can see that we're getting factors that are less than 2 if we do a really good job of determining what the capacity is. So let's take this 4,000 tons with the P over L ratio of 3. Well, that means we've got 3,000 tons of dead load and 1,000 tons of live load. We put that into that formula you just saw on the last page, and you wind up with a factored load of 5,500 tons. And for our 200-ton capacity pile, we multiply that by the P factor. We get 80 for a formula, and we get 150 for a static load test. And then doing the same computation, we wind up with the number of piles that are required. And we have almost a factor of 2 between a very inaccurate way to determine the capacity and a very accurate way to determine the capacity. So we've saved essentially 50% of the cost of the foundation. And a direct comparison, there you can see the number of piles in this theoretical example. It's pretty logical to do that with the LRFD in that we know the dead load, there's a lot of dead load on a bridge. So we don't need as many piles in the foundation to support the bridge. Let's take a look at an exercise that the Ohio Department of Transportation did over a period of 6 years. And we have the driven pile costs per year adding up to $124 million over the course of those 6 years. And the testing costs added up to $2.5 million, and the ratio of the two is we spent 2% of the driven pile costs in testing. Okay. What does that really mean? Let's come down and take a look at this table we just had before. And if we look at the relative costs, we call the formula factor of 1. If you take that ratio, which Ohio uses, by the way, 0.7 for the factor, which is a safety factor of 1.96, practically 2, that ratio 0.4 over 0.7 is 0.57. So that's my relative cost if I do a PDA. And so the complement of 57% is 43%. So that's my savings. That's what I have saved. And to put that in numbers, if that's 57%, Ohio Department of Transportation saved almost $93 million over that 6-year period by doing testing. They tested most every bridge that they put in. And Ohio, by the way, has approximately 27,000 bridges in the state. It's one of in the top 10 in the United States in number of bridges. Okay, we're going to shift gears now. So we're done with pile driving, and we're going to go to drilled shafts. If you put a drilled shaft in the ground, you drill a hole, no matter how you drill it, and you dump concrete in there, you don't have the same pre-manufactured quality that you have with the driven pile. And so we need to make sure that we have a quality project when we're done. And I can assure you that those shafts there were not designed to look like that. The one on the right, for example, was intended for a roadside sign that overhung a freeway. And you could imagine that if that had not been detected, a wind could have come along and collapsed the structure onto some unsuspecting motorist, and we would have heard about it in the newspaper about that. So it's imperative that we know the integrity of the piles that are being installed. So what kind of inspection is being done typically? If we drill a hole and we can look down it and visually inspect it, great. But a lot of shafts, probably even the majority of shafts, are drilled in a wet environment with a slurry. Once you have a slurry there, now I can't look down it anymore. So I have to use some type of non-destructive technique in order to evaluate the integrity of the shaft. So what options do we have available? We have pile integrity testing, cross-hole sonic logging, and thermal profiling are the 3 main ones. And let's take a brief review of some of those. For pile integrity testing, the idea is to put an accelerometer on the top of the pile, use a small handheld hammer and go whack, and look at that stress wave going down the pile and coming back. So here we have our input, and we have our reflection from the pile toe, and that's a good pile. We don't see any reflections coming in between, so it means it's a relatively uniform shaft. To get that, we had to apply some amplification factor as a function of time. In this case, 40 times. This is 40 times smaller in actuality. So if we hadn't applied the magnification, it would be very hard to see. Same site, neighboring pile, and now we see a reflection coming back early. So the same sign, this is the pile toe, so that's a tension reflection coming back. That's a tension reflection coming back. Tension reflection means we encounter something that is weaker than the section above it. So we can't have defects in the shaft. So that shaft would be probably rejected or replaced or repaired, depending upon the contractor's wishes. One of the disadvantages of this method is it can be confusing and it has limitations. Probably there's an absolute length limitation. That wave won't go forever. Sometimes they put it in terms of length over diameter ratio. Rule of thumb is beyond 30 diameters, you can't see anything. This particular one has 31 diameters, so yes, I can see something there. But one of the biggest problems that you have is that any major defect along the shaft, non-uniformity, will create extra reflections that mask the pile toe. For example, if the shaft has a large bulge, which often happens because you have soft soils, then that bulge creates a reflection that will mask the pile toe, and you can't pick it out from all the other wiggles that are coming in there. So it has a relatively bad reputation for this particular method. Cross-hole sonic logging came in about 20 years later than the low strain integrity testing. It made its entry into the United States about 1990. And the idea is you put a transmitter down one tube that's installed in the pile, and the receiver in the other one, and send a wave from the transmitter to the receiver, obviously, to look at the propagation of that, how fast it comes. How fast it comes would give you an idea of the wave speed. Better quality concrete has higher wave speeds. So there's a picture of the probes in the middle here. And the concept is you put water in the tubes, pull the things from the top to the bottom, and you can check if you have multiple tubes in the pile, all the different combinations, and look at the quality of the concrete by depth and by quadrant in the pile. And that's a field site there on the right. So let's take a look at some of the records. This is a 4-tube shaft, so we have 6 different profiles. And in each and every one of them, we see a defect down here between 28 feet and 48 and 40 feet. And when they cored the pile, they got down to 28 feet and found clean sand. So it wasn't a surprise that happened. So it's very good at looking at the quality of the concrete inside the reinforcing cage. Unfortunately, this is a test where we put a defect on the outside of the reinforcing cage. And there's my waterfall diagram. And I see no indication whatsoever of a defect. So this method is not capable of looking at the concrete cover, which is very important if you have a lateral impact or force on the pile. So that's its major flaw. So let's then turn to the new kid on the block, the thermal profiling. And it was developed at the University of South Florida, which is in Tampa, by Dr. Gray Mullins. The concept is concrete, as we all are aware, gives off heat during the curing process. And if we have a defect like a soil inclusion, the soil inclusion isn't going to give off any heat. So we can tell if we have good quality concrete, if we have high heat, and if we have a defect, it's not heating up. So that's the basic premise. Their initial concept was to use a cone penetration test with a thermal sensor on the cone to measure the soil temperature near the perimeter of the curing concrete. You can imagine that that's a rather slow process, so that never happened. Okay, but the concept is there. You know, we should be able to determine the quality of the pile just by some type of measurement of the heat content. As I mentioned, in 1990, the CSL access tubes became available. They were put in piles to check. There were more and more and more of them. And so by 1998, they said, why don't we measure inside the tubes using an infrared temperature sensor? Good idea. Problem with IR sensors is you have to remove water from the tubes. For the CSL test, there's water in the tubes. For the thermal test, there cannot be water in the tubes. So we have to remove the water. That's relatively simple to do if we have, let's say, a 40-foot long pile. But now start getting an 80-foot pile, 120-foot pile, 200-foot pile, these drill shafts oftentimes are. And that becomes pretty difficult. That's pretty difficult. In 1999, they did a lab test with their IR sensor in concrete paste specimen. So it's pure concrete or pure cement, no aggregate of any kind. And this was their measurement. And so they were elated that they said, we can do this. You know, it's going to take a while to get it to a applicable situation, but we can make the measurement. And notice in the measurement that the peak occurs at about 10 hours of time, and then it gradually cools off down towards the room temperature, which is the midline. This was their first actual test in a pile. They made a 12-foot long pile, 6 of it sticking up out of the ground and 6 of it's in the ground. It was again another concrete cement paste pile. And they put a IR sensor at the bottom of a 20-foot long PVC tube. So that was their measurement device. And here you can see it being inserted into a 24-inch diameter shaft. And here's the measurements that they made by putting it in and then rotating it in three different quadrants. And you can see that the temperature is actually 240 degrees. So they were really cooking the thing with pure cement paste. Okay. They got funding then from the Florida Department of Transportation, as we had done with our pile driving analyzer, the Ohio Department of Transportation, with the goal to better be able to detect the anomalies. They recognized that the CSL was very vague and that it gave no indication whatsoever of the concrete cover. While cover is not as important in Florida as it is along the West Coast, it's still important from a durability standpoint. They used it at the Alabama National Geotechnical Experimental Station in connection with Dan Brown at Auburn University. And that led them to a contract with the Federal Highway Administration to explore all the different concepts for integrity testing. Washington State, which is in an earthquake zone and is very concerned about the concrete cover, gave them a 2-year project where the objective of this research is to develop a reliable, practical, innovative, safe, and cost-effective method that can verify the shaft for concrete, as well as the presence of adequate concrete cover outside the shaft rebar cage. So they recognize that this has real potential to look at defects which are outside the cage. So these are some of their early attempts. They have something that would slide down an access tube. They put it in inclinometer casings. So they used an inclinometer sled with 4 staggered IR because they couldn't fit them inside the small diameter. They made a larger diameter thing, and the third generation is 3 feet long. Fourth generation is only 14 inches long, and you can see the IR sensors with the electronics that they had to package to make it all work. In 2009, they came to us because we had a reputation in the foundation industry for making testing products for foundations. Say, can you help us put this into a commercial package? So we repackaged their probe into a 5-inch long device. Again, there's 4 IR sensors on there. It goes down the dewater tube, and you collect the data from the top to the bottom. You measure the depth using an encoder. Cable goes over a wheel that spins, and it has 350, why 350 instead of 360 clicks per rotation. This was their signature test in the field back in 2005. The Gray Mullins had done, and he had installed defects outside the cage. And here you can see some of the defects there. So let's take a look at the one near the top. If you take a look at this, there's 3 tubes here, and tube number 3 is closest to a defect. And so tube number 3 is the red line, and we can see the reduction in temperature at that location. So yes, we can spot the defect. And the same with B. Well, with B, that's tube number 1. Tube number 1 is that one, and there we can see the reduction in temperature. And this was probably done at the peak temperature, and we'll get into that a little bit later. Had they tested a little bit earlier, they probably would have had even more definitive readings. Again, we got involved in the summer of 2009, and our engineers said, that using the IR sensor in the CSL tubes is kind of clunky. So they thought that we had a better idea. So we had a shaft that we already had a hole in the ground. So all we had to do was add on some defects on the outside of the cage and test it. And their idea was to put temperature sensors spaced apart along the entire length of the shaft and measure them continuously instead of at one specific time. So there's our prototype chain of temperature sensors, and here's the measurements that we made. The upper diagram, we put the sensors every 6 inches, and the lower diagram, we put them every foot. So let's take a look at our results. There's the first defect, which was put midway between the two, and we saw a temperature reduction both in the upper yellow string and the lower red string. For the defect that was closest only to the upper string, we saw a defect only in the upper string and not so much in the lower string. For the defect that we placed near the lower string, we saw very clearly the defect in that lower string, and not so much in the upper string, maybe a little bit of a hint. And for the one number 4 in the upper string, very clear indication of the defect, and a minor secondary effect on the other side. The shaft wasn't all that big. And the way the shaft gets rid of heat is laterally along the main length. At the top and bottom, of course, heat can radiate out through the top in the air or out the bottom into the soil. So now the device more currently looks like a small temperature chip on a wire that we encapsulate for waterproofing. And every foot there's a temperature node. They're attached to the rebar cages and then attached to a data logger for each one of those. And each one of those then send the data up into the cloud so that you can watch the temperature develop as the pile cures. So if you're an insomniac and want to get up at 2 o'clock in the morning in your pajamas, you can go look at the status of your shaft. When you take a look at the construction diagrams of the concrete take or overtake, each truck has a certain volume, and if you measure the depth after the pouring of that volume into the shaft, you can calculate the average diameter or radius for that particular truck, and that's what this magenta line is. If you take a look at the average from the thermal measurements, that's the black line, you see that there's a relationship between the two. And statistically, you can take the average temperature is related to the average radius. So any individual temperature you can get from that particular ratio, and find out that any particular radius on any quadrant at any depth in the shaft. So here's a case where we have an auger cast pile, 18-inch auger cast pile, that just had one single. It's not very big. It doesn't have a cage. So we put one thermal cable down the middle, measured the temperature, and we can calculate then the diameter of that shaft as a function of depth. And you can see the soils are clays and something that's more granular in between that has a bulge. Well, this particular shaft was excavated, and they could measure the diameter along the length. And here you see the comparison between the predicted and the measured diameter, and it's really quite good. That also helps you, by the way, if you put strain gauges in there to try to convert strain into forces to find the resistant distribution. Different states then got wind of this technique. The Iowa Department of Transportation contacted with the Iowa State University to test it out. They made a test with bags of clay spoils and attached to the inside of the cage, and also cured concrete prisms represented 5% and 7% of the cross section. And wire number 6 was located along the axis where these defects would be located. So let's take a look at the time history of the measurement for this. So this is at the very beginning of the pour. You can see at the very bottom, we have just a little bit of concrete put in there. And if I put this in motion, we're starting the concreting process. And every half hour, you can see the concreting pile was filled in 2 hours and 20 minutes. And you can already see number 6 is the red line, the defect. So even before they continue the waiting process now of concrete curing, I know that I have a problem. Now we'll just let it go, and every hour, these are by hour, and you can see very clearly those 2 defect locations. We have the sand up here, and we have the concrete cylinders down there. At 11 hours, that's when we could see them the best, which means the difference between the low temperature here and the average is the greatest. Down here, we have a cage alignment problem. You can see that some of them are higher and some of them are lower, so we have a balance there. If the cage gets shifted off center, then one gets closer to the center of the shaft where it's hotter, and one gets closer to the soil where it's cooler. So that's an indication of cage shift down there. Wrong button. Okay, so then we continue letting it cure for several more hours. And by that time, we can still see the defect, but it's much less. So The idea is that looking at it at what we call half peak time, or half the time that it takes to get to the peak temperature, is probably the optimum time to look for defects, which is the whole purpose of thermal integrity profiling. And there's the comparison between the half time, more or less, and the peak temperature time. And this shaft had two different diameters. And we can see that the temperature in the upper portion is warmer because it has more cover. And then it's relatively uniform along there, with still the defects clearly standing out. And true to contractor form, he put in an extra defect at no charge. They can't help themselves. Here's a project out in Washington State, I-5. And so I just show you an overall picture of the replacement bridge. And there's the results. And I think you're by now savvy enough to determine that we have a good pile down to this depth. We've got a 35-degree difference down there at dropout. And it's located near these particular wires. You can tell by the colors. And so we core it, and this is what came out, a bunch of rocks, which would, if you start loading the pile, and this is generally soft soil, bearing layers probably down here, you're going to probably have a settlement problem. One advantage of the cores, then, if you put a couple cores in, you can hydroblast the bad area and then pressure grout it to try to restore the integrity of the shaft. So, but you got to know that you have a problem in order to fix it. Project in Wisconsin, where they compared it with cross-hole sonic logging. Clearly, sonic logging showed a problem with all the perimeters and defects. And there's the drop off in temperature over the entire cross section. You know, every one of them was low. Pile was poured, good clean concrete above and below a 6-inch void. And it was due to a tremming problem that was noted in the construction logs. So, remember one of those things that the Washington State said that they wanted it to be cost effective. Well, is this a cost effective method? If you compare the cost of CSL on this particular project with TIP, and they did both, you find that the consumables, which would be the pipes and the pressure grouting to grout the tubes in the end, the average cost was $4,400. Average cost of the TIP to install the wires and the labor for that, $2,400. So there's a savings there. And there's a savings in equipment and engineering costs, primarily, I think, because we sent the data up into the cloud, and we don't have to be on the job site doing the testing. And if you add those together, the thermal integrity testing is less than half the cost of the cross-hole sonic logging, which is, or had been anyway, sort of the standard for testing drilled shafts. And you get the TIP results 6 days on average before they got the CSL results, and time is money. So in addition to an actual savings, they got a savings of speedier construction. So we'll try to summarize what we've done today. For the dynamic testing that Frank talked about, and I sort of finished up on it. It evaluates the capacity. It's relatively fast and inexpensive. For sand soil sites, the capacity at the time of testing, of driving the pile, is probably adequate. For clay sites where there's going to be a setup or a change in capacity, as Frank has pointed out, restrikes are very useful. 1 day restrike or you get more, that's great. We'll give you a better, more accurate capacity from the long-term perspective. And in any case, you're probably on the conservative side anyway, in most cases. And there are large savings from dynamic load tests through the code incentives. You can see that we can reduce the number of piles, which is reducing basically the cost, and you saw the cost savings that the Ohio Department of Transportation has attributed to the research that came out of CASE. So congratulations, CASE. For the thermal integrity testing, it uses the curing temperature of the concrete versus depth versus quadrant in the pile. You're testing very early after casting the concrete, typically between 6 and 24 hours. You have your result, and heck, even during the casting of the concrete, you already saw the defect appearing. So we can evaluate the concrete quality throughout the entire section, including the concrete cover. So that's the major advantage of this particular method. And we can evaluate the shape at the peak temperature time. You saw that diagram earlier. And we can find significant defects at the half peak time. You can find them at other times as well, but they're most obvious at that half peak time. Very cost effective. And it would be nice if the codes would use some type of reward for that testing. One of the reasons the dynamic testing took off is it got put in the codes. There's no current thing in the codes that talk about, well, you must do integrity testing. The thing that sort of drives the market there is professional liability. If you install a foundation that has a defect and it later has a failure that's attributed to your defect, now you have a problem. There could be something that puts a penalty if you don't do it. I can't imagine getting a plus if you do it. So fortunately, we have the insurance industry and lawyers on our side there. So I thank you. We both thank you very much for inviting us. It's been an honor really to do this. And you never know when your research could wind up being something like either of these two examples that's being used on a day-by-day basis and has really changed the industry for the better. So, thank you.
Any question? If you're bring up both of them.
Very short remark. Thank you for the best nostalgia that Fred brought us while he was talking. It's as many as the last 30 seconds. All what I can say is that we in the teaching profession are very happy when somebody, you are in a department store, knocks on your shoulder and said, "You remember me?" The roles have been reversed. Right now it's exactly the opposite. I'll tap on that shoulder and say, "You remember?" Thank you again. You do kids proud, you do the department proud, and above all, you do me proud. Thank you.
Yeah, definitely it's like a form university research to impact of application. I think I remember when I was a graduate student, when I read the first article, the case method, that was the first time actually I started to know case method. So that's the impact of research can have on the community. I think we have a lot of graduate students here and also undergraduate students as well. So maybe someday you work well, like settled with Frank and Garland, the role model. Maybe you have an impact contribution that make the department proud of you as well in the future.
Thank you.
Yeah, any technical discussion or career guidance questions, please feel free to bring up.
So I really like this both of your talks. I feel that very inspiring. because we do research all the time, but it's rare for us to think about how you really transform research to real applications and being so successful. I actually have a student who graduated last year doing biodegradation testing, and now he has a small startup. So I'm just wondering what advice you would have for him to keep up, and also, think about the competition in the future, how to build up your market, how do you, increase your customer. I don't know. So what kind of advice would you have for young students who are actually thinking about following your routes? Thank you.
You want to handle it? My first advice is patience. When you try to take a research project into actual application, Frank has often said it's a 20-year hurdle that you have to go over. And that's what it was with our pile driving analyzer with the thermal. Maybe we get that down to 10 years if we're lucky, but we're still in the penetrating the market. We've got to have good publicity. And one of the challenges that we faced back when I was just getting started in this, we would educate the engineers. You saw the seminars there. Well, every 5 years, you get a new round of engineers that you have to do the same education process again. It's like Disney in releasing their old classic cartoons. Every 7 years, they have a new generation of kids. It's the same way in engineering. So those engineers that you first train, they get moved up in position. It just takes a while. Going into and trying to affect the codes to make what you're doing a requirement is helpful. So, and competition helps as well. If we had remained the only people doing pile driving testing, we probably would have remained the only people doing it. But because we were able to have other consultants use our equipment on their projects, they then started saying, hey, let's do pile driving testing. So it wasn't just one voice in the wilderness calling out. It was a lot of people calling out that this is a method that works. So that's my advice. Patience.
Which is very hard. Right? We're in the digital age. I don't know how patient the young people are. I love 10 years to me. It's really a long time. So yeah, admire your dedication.
And you will see time flies.
Yeah.
You do something like that.
Yeah, yeah.
You think, my goodness, 2 years have gone by. What did I do?
Yeah, that's right.
So you have to, I think talking to the profession, talking to potential clients, talking to industry people in general is important to bring out your message, like Arlen said. Besides the seminars and the paper writing, then maybe even the ASTM is important to get your method documented and into standards.
I have a follow-up question to that regarding, did you find that you needed to find a business partner, somebody who was really very mindful on marketing the business so that you could focus on the engineering and the technical piece, or were you trying to do both of those?
Well, we were kind of lucky. I mean, Professor Goebel started with me, and he started actually the firms. He then later took another path, but he still stayed involved. Actually, he did a lot of talking to industry people while we were doing the nitty-gritty, the dirty work. He was doing some of this dissemination of the knowledge and marketing, you might call it. One of the things that we're lucky with is that he put us both in a position to continue working in these firms and working together. You said partner, yes, partnerships are important, but a partnership that doesn't work is worse than none. So we had the good luck that our partnership worked out perfectly. throughout the years. That's why we're here together. That's why we share this podium here today. So, yeah, partnership, if you have the right partner, that really helps because there's so much to do. There's development to be done. There's marketing to be done. There is the actual work to be done. And that can be overwhelming if you're by yourself.
Thank you. Yes, we just had a curriculum committee actually talking about teamwork, and this is something that as the current professors, we're always trying to bring in new ways to give our students that opportunity. And really, it's a learned skill. It's what we want them to know. They need to practice it. They need to think about how it has to be so much more than just the technical skills. We need to marry the two. And so
That's right. Yeah, you have to, and you shouldn't be afraid to start and doing something that you were not directly educated at. You have to get into these other fields that you mentioned too. You have to continuously learn and dare to do something different that you might, as an engineer, to sell something. That's a difficult thing. You don't want to talk about the pricing, it's dirty. So you gotta learn that.
yeah, very interesting. Thank you so much.
Hi, my name is Dong Fan. I graduated from this last December. I do have just out of curiosity, we see everything change fast in these days. We see so many different startups like every day. So what do you think will be the most significant change in civil engineering in the next 10 years or 20 years?
Your turn.
Good question.
Very challenging to answer.
Well, for sure, everything gets bigger and more expensive and faster. You have to keep out of the way of those who want to build something. Financing gets more and more complicated. But on the technical side, we're talking about AI all the time. How will that affect what we're doing? And might have an effect there. And there are some things where it would be really helpful. We tried it actually with our kind of work, using neural networks to do some of the things that the engineer is doing right now. In our field, though, to get 1 million pieces of valuable data points is practically impossible. First of all, with a variety of soils, machines, methods, it is virtually impossible to get meaningful sets of data that fit together. And then, there are other problems with it that it changes all the time what is being done. You have to retrain and then hope that it'll work out. So that might be something. So in various areas of construction and civil engineering, it might be the thing. And of course, you're already working probably with BIM and things like that, where there's this tremendous software available now. And for the practitioners, I'm glad I'm not into it. I'm out of it because it doesn't necessarily get easier. And to be able to use all of these tools to stay competitive will be very difficult.
I would add that if you take a look at some of the early slides that Frank presented, the basic measurement tools that we had then were crude, to say the least. As we progress through the years, it becomes easier and easier and easier to make a measurement. And I think there'll be more and more measurements in you name it, slope stability, whatever. We're going to see more and more of that because it's easier and easier. And you have to recognize that you're going to have to partner with somebody. You have to have good communication with the electrical engineers and the software people, because the software people are going to drive, all the hardware data collection, and so we need data, and that comes through measurements.
Sounds like we will have more powerful inspection tools and data analysis tools in the future. I guess.
Definitely. And we see it already that the instruments are building into the bridges. And the amount of data that you're collecting eventually will be also a difficult thing to manage. Because you can, like Garland said, easily measure now with much greater accuracy than was doing in the past. But then somebody eventually has to look at the results. Sense out of it. Good luck.
Thank you.
If I can make one short announcement. The Deep Foundations Institute, for all the students in the room, has a series of geotechnical scholarships, one of which was recently established in honor of Dr. Goebel, Frank Garland. The application is open now, largely for grad students, but I think also some undergraduates at the junior or senior level. That closes on the 15th of May, and one of them is at large, or several of them are at large, which means they go to university. So you have another week or two, please go there, look at the application, fill it out, because it's a relatively low effort thing that can get you a fair bit of money.
Does the Biodynamic Institute agree with consent?
It's DFI.
Oh, DFI.
Yep. We can talk after. Please do.
Yeah.
It's a great opportunity, and it's money that you wouldn't have otherwise. You can get it. Nothing wrong there.